Hello everyone, my name is Anurag Karmakar and I have got the opportunity to share the internship experience in embedded system. This presentation is based on everything I have learned during this program. First of all, the introduction to embedded system. It is used in microcomputer board connected to sensors, connected to actuators, real-time operation, and it is programmed once. Next one is the application of embedded system. Consumer electronics, household appliances, home automation and security systems, automotive industry, telecom, computer peripherals, computer networking systems, healthcare, measurements and instrumentation, banking and retail, and card readers. In these all types of instruments, embedded systems are used. Next one is the purpose of embedded systems. Embedded systems which are designed for a specific application contains application specific user interface aimed at a specific target group of users. Mobile handsets, control units in industrial applications, etc. are examples of this. Next one is the definition. Definition of embedded system: a combination of hardware and software which together form a component of a larger machine. Next is the classification based on deterministic behavior. These are categorized into two types. First is soft real-time system and second one is the hard real-time system. Missing a deadline may not be critical and can be tolerated by a certain degree in soft real-time system, and in hard real-time system, missing a program or task execution time deadline can have catastrophic consequences. Next is the application areas. In automobiles, engine management, trip computer; in building systems, elevator, heater, air conditioning; and in agriculture, feeding systems; in space, satellite systems. In automobiles, embedded systems are used such as trip computer, electronic ignition, immobilizer, keyless entry, ABS, ESP. In automobiles, such as in autonomous cars, electronic gas, electronic brake, and electronic steering. In automobiles, here we can see that a car with its 40 sensors and types of sensors are 25 at different locations are shown. Microcontrollers. The microcontrollers is based on a von Neumann computer architecture. CPU is the central processing unit. RAM or ROM memory can be used for data program, and input output such as keyboard and CRT screen. Next is microcontrollers, which consist of CPU plus timers plus input output, RAM plus ROM. It reduces chip count for board design, embedded system in today's technology, surface mount SMD, and ball grid array. Next one is the MPLAB IDE and X8 compiler and PIC-SimLab simulator, which is the microcontroller architecture. MPLAB IDE, a comprehensive development tool for PIC microcontrollers. X8 compiler is a C compiler for 8-bit PIC microcontrollers. PIC-SimLab simulator, a tool for simulating PIC controller projects. Here we can see the circuit diagram of PIC-SimLab 1, which contains ICs and many more other circuit components. Next one is the ROM. ROM consists of, or the abbreviation of ROM is read-only memory, PROM is programmable read-only memory, and EPROM is erasable programmable read-only memory, and EEPROM is electronically erasable programmable read-only memory. RAM. RAM can be changed anytime. Can stores program or data. Writing data to a location. All RAM data is lost when power is turned off. This is all about RAM, and I am aware of two types: static RAM and dynamic RAM. Again comes the address, which describes by the reference of RAM and ROM. RAM and ROM contains a large number of memory cells per chip. Size of memory cell is usually 1 byte, which is equal to 8 bits. And noting point is that K, the alphabet, must be in lowercase, not in capital. And 128K equals to 2 to the power 7 into 2 to the power 10 equals to 2 to the power 17, which indicates it is address lines. Therefore, there are 17 address lines required. RAM or ROM chips always comes in sizes of 2 to the power n bits. Address. Example of memory which falls under the category of address: for one address 2 data cells, for 2 address 4 data cells, for 3 address 8 data cells, and n address lines 2 to the power n data cells. Here is a summary of memory sizes. 1 KB equals to 1024 byte, 1 MB equals to 1024 KB, 1 GB equals to 1024 MB, and so on. Addresses of 8-bit controller: 16 address bits, maximum 6 KB memory size. 32-bit controller, which is the example: 24 address bits addressing single bytes, or 23 address bits addressing 16-bit words, maximum 16 MB memory size. 27 address bits will consist of maximum 128 MB memory size. Next one is the ROM implementation. Example: ROM with 8 bytes. ROM contents are memory 0 equals to 01, memory 1 equals to 02, memory 2 equals to 05, memory 3 equals to F2, memory 4 equals to 96, memory 5 equals to F0, memory 6 equals to 78, memory 7 equals to 3C. Again comes the ROM implementation, which is 8 into 3 ROM. Next comes RAM implementation, which is similar to ROM but replace connection element by active switch. Dynamic RAM needs refresh approximately 500 times per second. 1 field effect transistor is required. RAM implementation: SRAM, 6 field effect transistors are used. CMOS, complementary metal oxide silicon, which is the abbreviation of CMOS. Here we can see that the address lines and data lines are there. Next comes the input and output system. Input and output system consists of memory mapped, input output mapped, and DMA, which is direct memory access. Memory mapped versus input output mapped. Memory mapped is the input output device looks like regular memory cell. An input output mapped system provides input output ports with port address, port commands, often addresses for control register or plus data register. Commonly used for printers and modems. Input output maps. Memory mapped is used for video display. Input output mapped is used for input output address 3F8 to output. Address B800 0000 to B800 0F9F. Receive status is in case of input output mapped. And the last is the direct memory access, which allows input output devices to access memory directly without involving the CPU. DMA device acquires bus control and reads or writes data while CPU is doing arithmetic. Parallel processing equals to higher speed. If both CPU and DMA device want bus access, one has to wait a few cycles. Useful for block storage devices, example disk drives. For data transfer, we have to wait for the write sector to come around. DMA CPU does not have to wait. Interrupts when data is ready, transfers data, sets flag for completion. Here is the diagram of the direct memory access. So I have done with my presentation, and very much thank you to all who have listened to this presentation. Goodbye.